for putting together this great conference, and thanks for giving me the opportunity to speak. So I would say the first half of this talk, maybe some of you who've maybe seen me give talks in the last year have maybe seen before, but the second half is a little different. And I hope that, it'll be interesting to this audience. So what I'm going to do is I'm going to talk a little bit about polarizations and why people care about them. And then I'm going to talk about a characterization of polarizations of powers of the maximal ideal. And then I will connect that to triangulations. So to start, why would you care about polarizations? So the idea is you start with a square-free monomial ideal. You start with a monomial ideal and you want to find a square-free monomial ideal that sort of has all of the same homological properties, right? And so the first place that I am aware of that such an idea really appeared was in Hartshorne's thesis, where he sort of used this idea to prove connectedness of the Hilbert scheme. And so, yeah, he used something that was similar to polarizations to create these things called distractions. And that was the main tool that he used. It also gives you access to tools in Stanley Reasoner theory. So this is really great because now you can, maybe you didn't know how to study this monomial ideal that you had before. Now it's square free. So now you know that it corresponds to a simplicial complex and you can look at sort of topological properties of that simplicial complex. And it gives you back homological information about the ideal. This also appeared in work of Eremova, Herzog, and Hebe and Murai. They worked with these things called shifting operations, which are also a form of polarization. And then Nagel and Reiner used a polarization that I'm going to refer to as the box polarization to build a minimal cellular resolution for strongly stable ideals. But there hasn't really been, before, some of the recent work that I'm going to talk about, there hasn't really been a systematic study of polarizations. So first I'm going to establish some notation. So I is just a monomial ideal in this polynomial ring, and di is the largest power of the variable xi appearing in any generator. What I'm going to do is make this x check set of these double indexed variables. So there's going to be one of these sets for each of the variables in the original polynomial ring. And I'm going to put a second index now that ranges from 1 to this di, this largest power that appears. I'm going to make this new bigger polynomial ring out of all of these double indexed variables. Okay. And so an ideal I tilde in this bigger ring S tilde is called a polarization if you have this sequence of variable differences and it's a regular sequence. When you mod out by it, you get something that's isomorphic to the original ideal. And so you can see that these variable differences, all I'm doing is I'm sort of sending each of these double index variables to one particular variable in the double index set. And the point is that I should be able to do that for all of them. And then the thing that I get back after I do that sort of mapping should be isomorphic to the original ideal. What are some examples of polarizations? So if you're familiar with polarizations, you're probably familiar with the standard polarization, which sort of acts in the following way. It takes each of the variables, and then what you do is your second index, now you sort of want to separate each of these variables, right? So I have an x1 squared, now I want to separate it into two different variables. So I'm going to count up x11, x12, and then I'm going to start my count over when I get to x2. So it's going to be x21, and then I start the count over again when I get to x3. So it's 3, 1, 3, 2, 3, 3. The box polarization that was used by Nagel and Reiner is a little bit different. So it starts out the same, 1, 1 and 1, 2, but then now the next variable, I'm going to keep counting up. So it's 2, 3, 3, 4, 3, 5, and 3, 6, right? So this the second index of this last variable is going to be the degree of the monomial. And so in general, the way you want to think about this is you're sort of taking your monomial and you want to map each of these variables to a square free monomial that's inside that respective x check set. Basically that's what we're going to do. What we're going to do is we're going to view these monomials as the exponent vectors. Sorry. you're going to start with the input is going to be the exponent vector of the monomial, and the output is going to be this product of monomials, of this square-free monomials. And so we're going to view this as a map from those exponent vectors to the Boolean lattice. And so we're going to do this now for powers the maximal ideal. And so here I have a dilated simplex. And so I'm going to look at all of its lattice points. Okay, so that's what this delta Z and D is. I'm looking at all the lattice points of a dilated simplex, a dilated by D n minus 1 simplex. And so the point is that for powers of the maximal ideal, these are all the exponent vectors that you can get, right? This part's not super important, but you can take, this dilated simplex and you can kind of cut it by hyperplanes in all of the directions. And what you get is going to be this hypersimplicial complex. And what I'm doing is I'm only focusing on the one skeleton right now. Okay, so just focus on the one skeleton. And so every edge of this graph is going to be a linear syzygy edge. So the point is that each of these edges is going to correspond to a possible linear relation between the monomials with those exponent vectors, right? And so if you wanted to, and so this is sort of a picture of what it would look like in one dimension higher. So what we're going to do is we're going to put partial orders on the lattice points. And so the way that it works is you're going to say that with respect to an index that, A is greater than B with respect to index I, if at the ith spot, A is bigger than B, but in every other spot, A is less than or equal to B. And so in this example, sorry, I put all the videos at the bottom and I have to move them now. So in this example, you have, for example, 210 is greater than 120 with respect to the first index, because 2 is greater than 1, but then you see that 1 is less than or equal to 2 and 0 is less than or equal to 0. With respect to the second index, it's flipped, and with respect to the third index, they're incomparable. So the way that I picture this is with respect to the first index, think of the poset that's giving me this partial order is like this 300 is at the top of the poset. And then 300 is covering 210 and 201. And then 210 is covering 120 and 111, 201 is covering 111 and 102 and so on. So like when you look at it, you're looking at the poset with respect to the first index. And then you kind of imagine that you rotate. I mean, you're sort of acting by the symmetric group. And then now for the second index, you're going to be your poset, like the top of your poset is here now. And then for the third index, now the top of your poset is here. And so, so now it's a little more clear maybe why with respect to the first index, this one's definitely above this one. With respect to the second index, now this is the top, this one is above this one. With respect to the third index, these are both on the bottom level, so they're incomparable. So that's one way to see it. And so what we're going to do is we're going to think about these polarizations as giving rise to isotone maps with respect to the partial order that I just gave you from these lattice points to the Boolean poset. So here's an example. And so I'm only showing you what I did to the X variables, so to the first index. But what I did was I sent, so up here, I had no choice. This was 300. I sent it to X1, X2, X3. I sent it to all of the X variables that I had in my, now instead of double indexing, right? I'm having X, Y, Z, right? So I sent it to all of my X variables. Now here I had a choice, but it doesn't really matter what I choose as long as whatever I pick is contained in here. So I picked 1, 2, and 1, 3. And then down here, now this one, I have to make sure so that my map is isotone, that this one, whatever index I pick here has to be contained in here and in here. So I pick X1 because X1 is the only thing that's contained in each of these. And then at the bottom, I just get empty sets. Here I'm just showing you what happened to the X variables. And what we're going to do is you do this for all of the variables, and then you're going to delete any edges that that do not correspond to linear syzygy edges anymore. So one way to think about this, so here I'm deleting this edge, right, all these orange edges. So what I'm doing here is I have x1, x2, and then I know I'm gonna have a y variable, right? This is 2, 1, 0 here, and this is 2, 0, 1 right here. So 2, 1, 0, I have a y variable, and here I have a z variable. So before I had x squared y and x squared z. And those definitely were related by a linear relation. They only differed by one variable. Yeah.
Butter chicken. तू नहीं खाएगा? तू नहीं खाता? मैं उतना पसंद नहीं.
I didn't quite hear that.
I think this was only someone that didn't cut off their microphone.
Okay.
No question.
All right. Okay. So, okay, moving on. So now that I've sort of separated out all of the powers so that everything is square free now they're not going to have a linear syzygy between them anymore, because now they differ by y and z, but now they also differ by one of the x variables. So there's no longer a linear relation between these two. So I'm going to delete this edge. And then similarly here, this one, it corresponds to 1, 1, 1. So x, y, z. This one is 1, 0, 2. So before they differed by one variable, by one of the y variables. This one had a y and this one didn't. This one has a y and this one has two z's, but now they have different x variables, so they don't have a linear relation anymore. So I throw out those edges, okay? And so the question is, okay, now given, so you have this set of isotone maps that sort of maps each of the monomials that I have to, you know, a product of these square free monomials in each of these x check sets. How can you tell if it is a polarization? And so the theorem by myself, Gunnar Floystad, and Henning Lona is that the way you can tell is you look at each of these complete down graphs, we call them. So here it's just down triangles, but it, you know, this generalizes, you get these like down simplices in higher dimensions. And you look at the one skeleton and you want that the linear syzygy edges that are left after you apply the isotone maps form a spanning tree for each of these, right? So I should have had an example. I think that I deleted it, but I shouldn't have done that. But like, for example, you know, I could delete all of the bottom left edges. And if I did that, actually, that would be something that was up to symmetry equal to the box polarization introduced by Nagel and Reiner. The standard polarization actually doesn't delete any edges. If you draw in all of the possible linear relations between the generators, you still have all of them. But there are other combinations of things you could do, and that would give you a polarization as well. Okay, so now I'm going to shift gears into triangulations, but I guess, are there any questions about the polarizations half? I kind of flew through that. But yeah, the key ingredients are we have these isotone maps. We use them to map the monomials down, and then we draw in the linear syzygy edges that are allowed, and then we have this condition on the linear syzygy edges that tells us if our new monomial ideal is a polarization of the original one or not. That's sort of the summary. And so now I'm going to shift gears. I'm going to talk about triangulations of products of simplices. And so, yeah, so the triangulations of products of simplices are kind of magical. They kind of appear in all kinds of different places. It turns out that they're in bijection with all kinds of different things. They're in bijection with fine mixed subdivisions of dilated simplices by the Cayley trick, tropical oriented matroids, tropical pseudo hyperplane arrangements, matching ensembles, and more. And so there was this goal. So Galish and Neneshev and Postnikov sort of set out to try to axiomatize triangulations of products of simplices, okay? And their idea, they call these things trianguloids. And so I'm going to talk a little bit about their definition and then connect it to polarizations. So I'm using the definition that's actually not in that original paper by Galish, Neneshek, and Postnikov. I'm using the definition by Loho and Smith because I find it a little bit more tractable. So what you're going to think about is you're going to picture, so now again, we're looking at the lattice points of the dilated simplex, okay? But now at each spot, you're putting a bipartite graph, okay? And so, so yeah, this notation is just saying, like, if I'm looking at the bipartite graph at lattice point A, then if I ask for the neighbors of V, then I'm looking at the neighbors of V inside that bipartite graph A. That's what this notation is. And so they give these three axioms for a pre-trianguloid. The first thing is that each graph GA, so each bipartite graph at lattice point A, has a right degree vector A. So that's saying that, like, all of the vertices on the right-hand side of the bipartite graph, like if it's, for example, it's 2, 1, 0 is A, then the top one has, the top vertex has degree 2, the next vertex has degree 1, the next vertex has degree 0. So that's what they're saying there. Each graph has no isolated left node, so all of the things on the left-hand side of the bipartite graphs are always connected to something on the other side. And if you have two, what this is saying is if you have two vertices that are adjacent as lattice points, then whichever direction they're adjacent to each other, there should be containment in like, so if they're adjacent in, I don't know, direction 1, then it's saying that, so direction 1 would be like, okay, from the top going down, then it's like all of the vertices there. Let me show you an example. Okay, so here's an example. And so the first axiom, again, right degree vector A. So this is in spot 2, 0, 0. And so you see 2, 0, 0, 1, 1, 0, 1, 0, 1, and so on. All the left degree vectors so all the left-hand side vertices are connected to something. And then the third axiom is saying the following. So like these two are right below this one. And so it's saying that anything that this X, this one that I labeled X is connected to, anything that this X1 is connected to on this layer, it should also be connected up here. So here X is connected to 1 and it's connected to 1 up here. And then here X is connected to 2 and it's connected to 2 up here. And then now instead it's the same for the Y's. If you start here, now anything that Y is connected to here should be connected here and so on. And so already this is a little bit eerie because this looks an awful lot like the isotone map condition that we had for our polarizations. And I suggestively labeled these bipartite graphs. But so those were just the axioms for a pre-trianguloid. So they don't quite correspond to a triangulation of a product of simplices yet. They have this other axiom that I really don't want to get into because it's really tedious to check and it's kind of annoying to explain. But this last axiom, which they call the Hexagon Axiom, is the final thing that you need for it to be a trianguloid. And these trianguloids correspond to triangulations of products of simplices. But instead of explaining what this condition is, I'm just going to show you an example. So the example that I had before is not a trianguloid, okay? But what I'm going to do now is I suggestively labeled these bipartite graphs, and now I'm going to associate each of these bipartite graphs to a monomial. And so what am I going to do is if I have, an edge, then that's going to correspond to, like, for example, here I'm going to have x1, x2, here I'm going to have x1, y2, and so on. So I have a potential polarization, and I'm also going to draw in the linear syzygy edges, and it turns out that there are none of these middle ones. And so this is just the definition of those monomials. But sort of the punchline, and this appeared in my thesis, is that that actually these monomials that you get that correspond to each of the bipartite graphs are polarization of a power of the maximal ideal if and only if it satisfies axiom, the triangulated axioms 1, 3, and 4. So 2 was the one that there were no isolated left nodes. There's none of that is required, but 1 is the isotone map condition. Sorry, no, 1 is just saying that the degrees have to match up. So the monomial has to have the right first indices. This second one is not required for polarization. This third one is the isotone map condition. And actually what I show in my thesis is this fourth condition is actually equivalent to that linear syzygy condition in that theorem by me and Gunnar Floistad and Henning Lona. So actually, all trianguloids give rise to a polarization of the power of the maximal ideal. And instead of checking this kind of tedious hexagon axiom that's in that paper, you can actually just draw in linear syzygy edges and check the spanning tree condition, which is pretty cool. And then the last thing I wanted to say is that the other way is not true. Like I said, you don't need axiom 2. So for example, here's a polarization that's not a trianguloid. And so these dashed edges are deleted, and you see that I have a not mixed cell if you are familiar. So this sort of gives a hint as to why this polarization can't be labeled in a way that gives you a trianguloid. Okay, that's all I had to say. Thank you.
Okay, great. Let's thank Ayah.